So I've just copied this into a new file. I've copied the definitions because I wanted to start by some examples using the hand type, which was just a list of cards. So let's define a function, all clubs. All the clubs in a given hand. So it should take a hand as an argument and return another hand. It's going to take a hand and pick out all the cards which are clubs and return that hand. We don't care what the order is. So how do we define that? Well, the main mechanism we've seen for defining functions that build lists is to use a list comprehension. So we can solve this with a list comprehension. We have our cards. Let's call it CS. Our hand is a bunch of cards. And we're going to build a list comprehension. So every list comprehension has square brackets in it. And we're going to have a vertical bar. So we're going to build a list of cards, C. And where do the cards C come from? Well, the cards will come from these guys, the argument hand. But we're not going to take all of the cards. We only want to take those cards for which the suit of the card is equal to clubs. Okay? So there's a definition using a list comprehension. The generator is the list argument. And for every card that we take from the list argument, we keep that card if the suit of the card is equal to clubs. Okay, any questions? No? Now let's suppose somebody says, oh yeah, that's very good. We got all the clubs, but actually now we're playing a different game. We need all the spades. So what's your first temptation? You say, well, I've done something very similar to that before. I can define that quite easily. I can cut and I can paste. There's a lot of cut and paste that goes on in beginner programming and in real programming too. And I want to change this to spades. But I don't want it to be equal to clubs. I want it to be equal to spades. And you say, there you go, done. Super. Now that's fine. You'll get something working, but it's not a good way to program. Or at least stopping there is not a good way to program. Because whenever we do that kind of cut and paste operation, we're taking a pattern of computation that we've done before, and we're saying, I want to do something similar. So I make a copy of it, and then I change the bits that I need to change. But what it also means is that any mistake that I made in the original one, I've kind of cloned that into the new one. So now, if I have to fix a mistake in the original one that is also in the new one, I now have to fix two mistakes, not just one. So mistakes are propagating. But also, if I decide to change my data type in some way, for example, I decide, oh, I don't want a type synonym here, I want a new type, some other kind of structure, then now I have to also change these in two places to implement the same single change. So in the long term, I've made the code a bit harder to read, but I've also made it harder to maintain. So whenever you find yourself doing cut and paste, you should step back and say, okay, that works, but can I now rewrite the code so that it doesn't have this common similar bits of code? Can I turn this two similar things into one thing? So how do you take two similar things and turn them into one thing? Well, you think about which parts are different. Which parts are different between this and this? The only thing that's different is the suit. So we can make these into one piece of code rather than two by making a function. And I'm going to call that function select. It's going to be a function to select all the cards from a given hand that have a given suit. So here's the type that I'm going to use for my select. instead of a function from hand to hand, it's going to be a function that if you tell me what suit you want and you give me a hand, I will give you back all the cards in that hand which have that suit. Okay? So the parameters are the suit S and the cards. Now this is one more final cut and paste. This is the good cut and paste, because this is the one that I'm going to use to re-implement this. I'm not going to test whether I'm the same as spades. I'm going to test whether I'm the same as this parameter S. And now instead of all spades, I can just select the spades from the cards and select the clubs from the cards. So I've done some cut and paste, but then I realized what I actually needed was a more general function than the ones that I started defining. So I've now, these are just special cases of the select function for selecting a given suit. Any questions about that? So whenever you see cut and paste code in your solutions, try and think about how you can remove the cut and paste by defining a more general function. It's usually the right thing to do. It usually makes your code easier to modify and easier to maintain. Okay, let's talk about lists. We saw in the Kahoot a few moments ago that there are a couple of operators, very simple ones. Operators. There's an operator, which is usually called cons for constructing a list. So this is called the cons operator. And the empty list. Now, why have I picked on these? Well, they're the very basic building blocks for lists. In some sense, all lists can be thought of as being built from the values that are in the list together with these two basic operations. So, for example, when we have a list 1, 2, 3, really that's just the same as putting 1 on the front of the list which is built by putting 2 on the front of the list which is built by putting 3 on the front of the empty list. They're the same things, and this operator groups to the right, associates to the right, so I don't need any brackets when I write that. So all lists really can be thought of as being built by two basic building blocks. The basic building blocks of a data type we usually call the constructors of the data type, just as we did when we described new data types like suit and rank and card. Each one of those has constructors, which are the building blocks for values of that type. The only basic building blocks for building lists are this one and this one. Operators like the append operation are just functions which are defined in terms of the basic building blocks. So this is not a primitive, this is not a constructor, this is just an operator, a function that can be defined using these basic building blocks. Okay? Okay. So let's take some examples of functions that are already predefined. So these predefined functions, they actually all live in a module. And that module is called the prelude. We've used other modules. For example, we've used QuickCheck, which lives in a module called test.QuickCheck. We had to import that module in order to use QuickCheck, but the prelude are the functions you get without having to import anything. They're kind of already pre-imported. So we can talk about functions from the prelude, and I mean the predefined functions, but they're not built into Haskell. They are just functions that are defined in advance. So null is a function which tells you whether a list is empty or not. Yes, that's null. No, that's not null. So let's define null. Now, since it's already defined, it's best not to try and define it again because Haskell will get confused. Which null did you mean? The one in the prelude or the one that you just defined? So I'll use, whenever I'm defining a prelude function, I will use a prime and give it a new name, null prime. It's similar to null, but I'm defining it. So how do we define functions on lists? Well, we use pattern matching. And the pattern matching, the patterns will involve the basic constructors. So if it's an empty list, then the answer is true. But null for any other kind of list will give you false. So there's a definition of the null function that returns whether a list is empty or not. Head and tail, two other useful functions, but not that useful. I don't want to see them too often in your code, and the reason is because they're not very reliable. Head takes the first element of it, gives you the first element of a list, and tail gives you the rest of the list. And the reason they're not so useful is because most of the time we use pattern matching, but the other reason is that they are not safe functions. If you apply them to if you apply head to an empty list, you get an error. And if you apply tail to an empty list, you also get an error. And errors are not something we can recover from. We can't give an error in the middle of our Haskell expressions, at least not for the bit of Haskell that we're looking at now, and recover from that error. We need to avoid errors. Question? If you use tail on a list with only one element, what do we think? We get an error? Yeah, if we have a list with n elements, we take the tail, we get back a list of n minus 1 elements long. So if we start with a list of 1 element long, we'll get back a list of 0 elements long. There is only one of those. It's the empty list. So it's the sensible thing. So let's define tail while we're here. I'll call it tail prime. Tail prime, if you give it a list that has this shape, x on the front of x's, then it gives us back the x's. So that's a typical definition using pattern matching. We show this is the pattern, the shape of the list that we're interested in. This is a list whose first element we're calling x, and the rest of the elements we're calling x's. And the answer will be not the first element, but the rest of the list. Now, if we follow our usual convention, our usual style, we inform the reader of this code that we don't care what x is by writing underscore. And head is very similar. If we have x on the front of I don't care whatever list it is, then we just get back x. So now these will behave the same as head and tail in the prelude. The error messages we get won't be the same because I haven't given this, I haven't told this what to do in the empty case. So if we take tail prime of the empty list, we'll get an error, and the error message will refer to the fact that there's non-exhaustive patterns in function tail. So the error message won't look the same, but it will do the same job. Any questions? Yes, question up front.
Why did you use parentheses?
So the question was, why did I use parentheses? So when we define functions and we have patterns, if the patterns are not simple, like just a variable x or an underscore, then we always write brackets around them. Because if I don't write brackets around it, what happens is that actually Haskell will think this is a function that has 1, 2, 3 arguments. It will think that this is the first argument, this is the second argument, and this is the third argument. And that's because the operator precedence is never as high as a function application. So for that reason, we always need to put brackets into our arguments, for the same reason that we put brackets when we write even 1 plus 1. Is 1 plus 1 even? That's true. Well, if we leave out the brackets, all hell breaks loose, because it thinks that I'm applying even to 1 and then plus 2, plus 1 to that. So it all gets very confused. So the brackets are here for the same reason brackets are in these definitions. Thanks for the question. Any other questions? All right, let's talk a little bit about types, because I didn't put in the type signatures for these guys. So let's put in a type signature for head. So head is going to take a list of, what should we say, int. Yeah, I'll get there. Wait for it. So here's a type that we could give to our head function. If we give it a list of int, what do we get back? What type is the first element of a list of int? It's an int. So that would be a type we could give to the head function. And Haskell will agree with it. It won't complain. But there's nothing in the definition of head that sort of says that it has to be applied to ints. It should work on a list of anything you like. So it would be a shame if we had to define 20 different versions of the head function, one for int, one for string, one for bool, and so on. There are programming languages that have types that forced you to do that kind of thing, or worse, in their early design. Java is a good example of that. The early versions of Java, there was no way of saying this is a function that works for any type. The way we do that in a type is to use something called a type variable. That is, we use a variable name that stands for a type. I'm going to use the variable name t. So t here is a small letter t, and this says, give me a list of any type things you like. It doesn't matter what it is, any t you like. And what you'll get back is a single thing of that type. So if you give me a list of ints, I'll give you an int. If you give me a list of bool, I'll give you a bool. Give me a list of string, I'll give you a string. You get the point. So we use a type variable in the type. And that's called a polymorphic type. So that means we can apply head to not only a list of numbers, but a list of bools or a list of bools, and make a list of bools, if you like, and so on. Okay? So that's a type variable, and a type that uses type variables has this fancy name in Haskell, and that's polymorphic types. When you learn Java later, you'll see that they're called generic types in Java. And generic types in Java were more or less designed by the designers of Haskell and added to Java in the same kind of style. Any questions? All right, we're going to take a jump now. Yes, sorry, question. If we only want to accept integers and floats, yes. So there is a way of saying, I'm going to work for any type you like, but providing you're a type that is in a certain gang. Okay? So in Haskell, there are these gangs of functions, or sorry, gangs of types. You think of Hell's Angels as a gang. They all have something in common. They all like Harley Davidsons and organized crime. Okay? So being in to be in a gang, you sort of have to have something in common with everybody else in the gang. In Haskell, all the types, many of the types form little gangs. These gangs are not actually called gangs in Haskell, they're called type classes. But think of them as gangs, and everybody in the gang has something in common. I'll give you an example of a gang, and that is show. Show, with a capital S, is a gang. You can be a member of the gang show, you can be a member of the type class show, if you have a function called show for converting yourself into a string. Okay? So if you're one of those types in that gang, then we know you can print out your values on the screen because we use the show function. So that's what we were doing when we were saying deriving show and deriving EQ. We were saying make this guy, make this type a member of this gang. And to do that, you need to give them a Harley Davidson and a flick knife, or in this case, a show function or an EQ function. Yes, question? So the question is, do they become a subtype of the type show? So this is where we get into dangerous waters, because if you know a bit about object-oriented programming, which maybe a third or half of you do, then you might think that the notion of class here is like classes in an object-oriented language. And that's not the case. So if you know something about object-oriented programming, a class in Haskell is more like an interface. If you don't know anything about object-oriented programming, don't worry. It's fine for now. Okay? So the question was, about an hour ago, can we sort of restrict this to say, I want it to work not just for int, but I don't want it to work for every possible kind of type. Can we just make it work for some types? And the answer is yes, we can make it work for a gang of types. We can make it work for a type class. So if we wanted a function that said, I only want to allow head to be used for lists of numbers, then I need a gang for numbers. There is a gang for numbers, it's called num. If you're in the num gang, that just means we know how to do plus, minus, multiply, and all those kind of things. So here's how we would write the function that says, this is a function from lists of t to t, but only when t is a number. It's in the number gang. This means it will work for int, it'll work for integer, doubles, floats, and so on, but it won't work for bool, because bool is not in the num gang. Okay, that was something I wasn't going to get into today, but we will get into it probably in the next lecture, so you've had a little brief taste of that before we start. Okay, I want to move now on to talk about recursion, and I haven't got much time left, so maybe I've got 5 minutes left. Do I really want to talk about recursion? Let me give you one example, and we'll pick up with that next week. You remember recursion? Here's a recursive definition of factorial. I defined it slightly differently last time. This time I've combined one equation using pattern matching. What do you do when you take the factorial of 0? And one equation using a guard. What do we do when n is bigger than 0, the factorial of n? And we've taken the big problem and worked out how to solve the big problem by solving the slightly smaller problem, factorial of n minus 1. And how do we do that? Well, we multiply by n. When we define functions on lists, we can define functions in the same way using recursion, except the base case is not like the base case for numbers, which is 0. The base case for lists is when you have an empty list. So let's talk about the size of the empty list. How many cards are there in the empty list? There are none. What about the size for something which is bigger than the empty list? What does something that's bigger than the empty list look like? Well, it has at least one element, let's call it x, on the front of some list, which may or may not be empty. So every empty list has this pattern, looks like this, and every non-empty list has this pattern. So we're going to use recursion to define size, not the only way. And so what we do when we use recursion, we're using primitive recursion. We try and work out how to define the size of a list with at least one element in it in terms of the size of the rest of the list, ignoring the first element. So if I know the size of the rest of the list, how do I work out the size of this list? So I've worked out the size of the tail of the list. It's 200. It has 200 things in it. But what I want to know is not how big this list is, but about how big this list is. One element bigger. So what do I have to do to that value to get the size of this one? I have to add 1 to it. I add 1 to the size of the slightly smaller list. So this is an example of a recursive function over lists that works in a similar way to recursive functions over numbers. We specify what we do in the base case, and we specify what we do in the non-base case in terms of solving the problem recursively for a problem which is one bit smaller. I'll leave that for you to chew on until the next lecture, when we'll do more stuff with lists. That's all for today. Thank you.